So now the one of the topics that came up in the debate is the temperature and the composition of the sun, or well, I guess just really the sun in general. So I'm wondering if you can kind of tell us more about like how do we know what the temperature and the composition of the sun is?
It's actually one of the few areas of astronomy that we can be super precise with. I mean, astronomy is hard because we're trying to observe the universe from this tiny little dot. Now, that does not mean that we're unsure about the shape of the Earth. No, we know what's happening. But in terms of you want to look at distant galaxies and figure out exactly what's going on, it takes a lot of effort. But in terms of the temperature and the composition of stars, in particular our sun, because it's so close or relatively close to us, we can do that very, very easily. Well, easily compared to other things, and science gets very hard very quickly. But this is something that I covered in senior physics, where you can do this by simulation, you can do this, and then you can actually go and test all of the individual components. And it comes down to Boltzmann distribution. And I know that she mentioned, second law of thermodynamics, because gas pressure, that seems to be a very common one. So most flat earthers should at least accept Boltzmann distributions but that you can use that in a way to actually do that for the color and the intensity outputs at different wavelengths for certain elements, certain bodies that are hot. And then you've also got black body radiation. So you can actually put all this together. You can look at the emission, you can do the maths, and it's kind of a balancing act between a number of different formulas and get this nice graph that tells you exactly what you should see for different colors. Then you can go and test that and find out exactly what the composition of the sun is. And on top of that, there's wavelengths missing because different elements, and they're all going to be elements at the temperatures of the sun. You're not going to get many molecules, things will break apart. You can actually see these lines, the Fraunhofer lines, they're called, in that spectra where you've got missing bands of light, so missing colors. And those colors correspond to their elements. And you can do that test here. I've actually built a spectrometer and looked at what the emission of these are. You can also then use it the opposite way and see what wavelengths are missing. It just kind of, you spread the light out, and that's the basic one. Or you can get a computer and you can start doing things more accurately. So you can look not only what the actual sun's made of, bits and different parts of it, but then you can look at what's around it. And you can do this for quite a lot of different areas. But the sun is one in that kind of a mix of spectroscopy, the field that I don't think it's quite mentioned, but they were talking about the field differently in the video. And that's what it is. And if Rose is talking about people doing the experiments, I've done those experiments. I've run the simulations, I've done the experiments, I've built the spectrometer. So again, I'd be very curious as to what she has to say or what flat earthers would say to that.
Well, I mean, they would obviously say that the sun isn't really, performing nuclear fusion, and that it's really local, and there's something called a luminary.
But I think that the sun and the moon are luminaries. I have no idea what they are. It drives me crazy. I hope that within my lifetime I get more answers. But I think that they are going around the Earth. They're navigating around the Earth. And I also can gift you an app that can show you more about this. But they're much, much closer than the mainstream model wants you to believe.
I'm not exactly sure what that means, but apparently, at least for her, she thinks that it's this luminary in the sky, and it's actually local. I'm wondering, given your expertise, what would the ramifications of the sun being closer to the Earth or being like smaller and local? Like, I mean, do you think that it would result in the typical flat Earth depiction of it, where like it only lights up half of the Earth, and it's in perfect, synchronous orbit in the upper atmosphere?
Yeah, it just wouldn't work. You could almost put any aspect of that model, and it doesn't work. The idea that the light would travel different distances, for example, and I've got it illuminating exactly half the planet, they still have to describe that. And if the sun is really close, it just wouldn't happen. There's nothing that's going to block the light so evenly. But if it was close, it would have to be very small. And as I mentioned, we have a very good understanding of what the sun's made of. We can see what's on the outside. In fact, helium gets its name because it was first discovered in the sun before we discovered it here on Earth. There was a missing wavelength in the yellow. There was this yellow band that was missing. And they're like, that they spotted. And it was like, what's that? And they went looking. They thought it might have been sodium. That turned out, no, it's helium. So we can do those experiments. If the sun was close, then the way it produces energy and the heat that comes off it would have to be generated completely differently. But we know how it works in terms of fusion. We've done fusion here. We don't have it working as a power source, a viable power source yet, because it is very hard to do. But we can still fuse hydrogen into helium. We know what happens. We're well aware of that. We can do the maths for it. We can actually do the experiment. There's one in America, I believe, the National Ignition Facility, that uses a giant laser to do it. I think it's really cool. It's the world's most powerful laser. They actually tear the atoms tear the electrons off the atoms in the atmosphere if it was any more powerful. That's how strong the laser is. Sorry, that gets me. I'm sorry, a bit of a nerdy scientist, but I guess that's the whole point.
Yeah, yeah, it is.
But all of that, all of our understanding of things that we can do, things that they can look up, would have to be different. Because fusion, we know how much energy it takes to fuse two hydrogens together. So we know then what kind of forces from gravity, how much pressure we need on that inside. We know what temperature you need, and you can do the calculations. But okay, a star this size is going to fuse and do this. And you can do the calculations and figure out what size stars are going to fuse up until you get, I think, which ones are actually going to fuse, which ones aren't. So you get like brown dwarfs, you get stars that fail, that don't actually start fusion. You get some like our sun that, they'll fuse. It'll eventually get up to carbon and then it'll run out of fuel. Nothing will happen. Our sun won't go supernova. But if you get a really big star, then it goes supernova. We can do those calculations and we can go looking at all the stars around us. We can see that. We can see what kind of ones are doing exploding, which ones are not. And by exploding, I mean supernova. We can do all that. But if the sun was close and the stars were not, then all of that goes out of the window. And we can test almost every aspect of that. And the moon can't be a luminary.
Yeah, that kind of gets into another area because she mentioned the cold moonlight.
It turns out that moonlight is colder than the shadows at night. So if it's the sun that was reflecting off of the moon, and I already brought up another reason why we can show that the moon is possibly giving off its own light, but that's also to explain, because you're like, how could it work? Like, why would we see the moon at night? But why would the moonlight be colder if it was the sunlight hitting it than in the shade?
And with so what I understand of light is that when the fusion happens in the sun, light is emitted in the form of a photon. And when that travels the 1 AU or average 1 AU to the Earth, and then once it actually hits an object, it transfers a little bit of energy before reflecting off of it, and so it like light literally cannot be a cooling light like they say, because she says that the moon has cooling light. And she's done, the experiment, she claims to have done the experiment where at night when the moon is the moonlight, things that are hit by the moonlight is actually colder than things underneath the shade. And I'm kind of wondering if you can give your thoughts on that.
Yeah, that's a very common experiment that flat earthers like to bring up. And there's a couple of problems. One, as was brought up very well in the debate by Mark, was the accuracy of the thermometers. And at least Rose accepted that she did not have the right equipment to do that one. So I'll give her bonus points for that. What What often happens, though, is that they ignore the other physics that's going on. I'm very curious if they did it with an infrared camera. I reckon they'd get very different results. So the reasons as to why it's not a valid experiment comes down to radiative cooling. There are objects around the thermometers or around whatever they're aiming the thermometers at that are also different temperatures. So if you've brought something from inside, you brought it out at night, you might have all the objects around from the day that are still warm. And so if you put something in the open, it just radiates out normally. But if you put it next to other objects, you put it in shade, it's going to be affected by those objects. Those objects are going to have their own temperature and so will be giving off photons, but in the infrared. And if they're giving off less than what else is in the environment, then that's going to mess with it if they're giving off more. So a lot of the times the flat earthers will get that wrong because they won't take radiative cooling. And I've heard some just flat out say, no, that's not an answer. But we also know how light works. You were mentioning that light gives energy. Every a photon will have an energy determined by its frequency, E equals HF. One of the easiest formulas because there's only 3 things in it, which I like because that way I haven't forgotten it. And H is a constant. So there's only 2 things that change, either the frequency, so the color or wavelength of the light, and its energy. You can't have either of those things being negative, which is what you'd need for moonlight to be cold. So it would go against everything we understand about light. And it would go against entropy as well, which also comes back to the laws of thermodynamics. So I'm assuming they would at least give some credence to at least the laws of entropy. You cannot radiate cold light. 1, light can't be cold, and 2, you can't radiate coolness. It goes the other way. You can only radiate heat outwards. The only time that you can cool, or the only time that I'm aware that you can cool something with light is when you do laser cooling, but that's a bit different. That's relying on a few really, really weird and wacky quantum mechanical operations. And what you're essentially doing is stopping your atoms from vibrating. But this does not work with moonlight. This is done in controlled laboratories with lasers where you trap small individual particles. Radiated light just coming out from the moon is not going to do that. It's not capable of doing that.
Now, one thing that she mentioned that I really didn't understand what she was talking about was when she talked about the possibility of the moon reflecting the sun's light. She just said the inverse square law, and like that was it.
It's so crazy. I think that the moon is creating its own light, and you can look at the inverse square law to learn more about that. I have so much to show you. I'm going to send you a whole entire document with all this information.
And so I'm wondering, do you know what she might be talking about with that?
I have a feeling I know what she was talking about. So the inverse square law has to do with the intensity of radiation coming from a point. You can also use it, it's actually better used for energy. So it also works with sound, things like that. And it comes from the surface area of a sphere. So imagine I've got all my energy and we're starting from this point. So let's say I've got my point and I'm going to generate some energy out of here. So it comes out of here. If we think of a flash of light, it's going to start expanding and it'll be spherical in the way it expands as long as we don't have kind of atmospheric distortions. But over the distance of space, well, it's a vacuum, so it's not going to affect that. And even when it hits the atmosphere, it won't be affected by that. But as the energy spreads, that sphere is getting bigger. It's getting bigger, which means that energy that was once starting in that small little sphere is now covering a much wider area. And the surface area of the sphere is proportional to its radius squared. So the further you are away, the bigger the sphere. So the more spread out that energy has to be. So you end up with the inverse relation to that. As the radius goes out, the energy is going to go down as 1/r squared. And the only thing I can think of that she was referring to that is that somehow that law means that the radiation from the sun cannot be responsible for what we're getting off the moon. Either the moon was not bright enough or that it should be brighter. I have the feeling it'll be the former. I'm not entirely sure what's meant by that, because there's a few things to take into consideration, and that's the distance between us and the moon is negligible compared to the distance between us and the sun, for just dealing with inverse square law. And so for most of the time, the sun reaching the moon has about the same intensity that it is when it's reaching us. But the moon's not a mirror either, so it's not going to be perfectly reflective. As you mentioned earlier, some of that energy when it's reflected is lost. So I'm not entirely sure what she was talking about, but I think that has to do with it. But you can do those calculations and it works well. There's nothing wrong with it.
Well, I think that and of course she didn't say this, I'm just purely speculating, but I feel like her misunderstanding of it comes from her thinking that, the sun is supposedly 93 million miles away, and so whatever light is being emitted from that distance, there's no possible way that it could reach the moon. And I feel like her mentioning the inverse square law is her trying to give some kind of like mathematical teeth to the idea that the sun would just be too far away to really have any light that we can see. But I really think that kind of shows how she doesn't really understand how light works in general. Because I don't see a problem with the sun being 93 million miles away with the amount of energy that it regularly puts out. I don't see a problem with it being able to, with it being able to, one, reach the Earth, and two, being reflected off of the moon back onto the Earth. So I feel like that's the fundamental misunderstanding on her part, is just exactly how powerful the sun is, how light works, and how that distance really doesn't exactly matter in this particular instance.
Yeah, I think that goes back to what we were talking about earlier, that we know how a lot of this works. We know how the sun produces its light. We know how bright it is. We can work backwards. And yeah, that light should reach us. I mean, it does. I don't know why they think that if we were going to make up, or if the professionals are going to make up all these models, if the authorities are going to make up these models and light, why would they put glaring holes that are that obvious in it that you can do with rudimentary maths? I don't see how that would work. But the sun is very, very bright. I mean, Newton famously temporarily gave himself eye damage. He blinded himself by looking at the sun through a mirror. Not one of his brighter moments. Sorry, the pun was not intended. I just realized that. I mean, that's up there with him also shoving rods under his eye and pushing on his eyeball to see what happens when he changed its shape. But the sun is very bright, and we can. So I'm not sure how the inverse square law would come into that anywhere. It reaches us. We know its distance. We can figure out the brightness.